guys, welcome back to my YouTube channel. Again, my name is Rica Casabuena from ECE31, and for today's Digital Electronics Laboratory episode, we will be having our experiment number 5, which is our 8-bit analog input, which can be further understood using our website here, which is the Microchip Developer Help, which will allow us to further understand how should we perform the experiment and what is the proper connection of our circuit components to our IC, as well as on our breadboard, as well as the step-by-step procedures using our Mplab software. So you can just go to this site and then read this experiment to further understand our experiment for today. So to give you a heads up, our objectives for this experiment is that are, number 1, to construct an analog input that can control an LED as the digital output using a potentiometer. Number 2, to understand the principle of varying the voltage dissipated to a circuit using a variable circuit component such as a potentiometer. And number 3, to know the principle of how microcontroller reads or process analog input, which will be given using our potentiometer. So stay tuned and we will be proceeding with our Mplab software. Now, to explain the principle behind our project, okay, before we proceed to the Mplab software, we can see here that signal voltages are not always digital, such as 0 or 5 volts. So it's not always digital, meaning it's not always a binary number like 0 for 0 volts and then 1 for 5 volts. It's not always like that. So many times they are analog, meaning it is continuous in value in terms of time compared to our digital signals. Okay, let's say for example signals which is discrete in terms of time, meaning there is a specific value or an exact value, let's say 1 or 0, compared to analog or continuous, which may contain decimal values and is not an exact value. Okay, that's the logic behind analog and digital. So in these terms, okay, if it is an analog, in that they can vary in voltage level. So our voltage level will not be fixed. It will not be fixed 0, it will not be fixed 5 volts, but it can vary in value. And that is where an analog to digital converter is used to convert the input signal from an analog voltage level to a digital value that the microcontroller can process. So before the microcontroller process our input signal, it needs an ADC, okay, an ADC or an analog to digital converter, which can be used to convert it, okay, from analog, commonly, okay, from analog voltage level to a digital value that is being processed by our microcontroller. So this experiment will let us monitor the controlled voltage from using our potentiometer, okay, and that can turn on or light up our LED when our threshold is crossed, okay. So to provide you a heads up, okay, we will be using a potentiometer, which is this one, as you can see on your screen, which is a 3-terminal variable resistor. Okay, it is a kind of resistor, meaning it provides a resistance to our circuit, in which the resistance is manually varied to control the flow of electric current. So how do we vary the resistance to our potentiometer? So we just manually turn the knob, okay, this one. We just manually turn this knob to increase or decrease the value of our resistance. Okay, so typically a potentiometer acts as an adjustable voltage divider. So that's really an edge of the potentiometer as an electronic component. That's why it is used in circuits where varying of voltage is necessary. So with this project, we are expecting that we will be able to create an analog input to read our potentiometer, and with that, we will be able to control the LED as our digital output. Okay, so expecting the result of this experiment when the potentiometer is turned right off the center position. Okay, so when we turn the knob to the right from the center position, okay, the LED will be turned on or it will light up. But when the potentiometer is turned left off the center position, okay, when we turn the knob to the left, then the LED will be off. So that's our expected result or outcome in this experiment. So now let's proceed to our Mplab software simulations. We'll be proceeding to our Mplab software, and then let's create a new project here. So it should be microchip embedded and then a standalone project. Then let's click next. And then we will be using our IC, which is a PIC 16F, okay, 18875. Okay, let's select this one. This is the long IC, and then let's click next. And then let's select our compiler here. And then let's rename this analog input, okay, analog input Casabuena. And then let's click finish. So let's just wait for our software to properly load up. Okay, so let's go to our MCC file here to edit our configuration. So let's just wait for it. So let's save this one. Okay, let's select the proper package for our IC, which is the long IC here. So if you can still remember, I told you a while ago that we will be using an analog to digital converter to convert our analog input to digital one. So we will be adding this analog to digital converter, which can be found here in our device resources under peripherals. And then let's double click this one, and then let's add this one. Okay, so it's added already. As you can see, it is already here on our peripherals. So once our analog to digital converter has been added to our peripherals, let's go to our pin manager here. Okay, we will be using the port A0. Okay, here, this one, and we will be considering this as our input. Okay, as our analog input. This ANX here should be green. Okay, as you can see here, this pin number 2 has been turned green, and after that, okay, we will be considering. Okay, let's scroll this down. We will be considering the port A. Okay, port A4. This one, that one. Port A4, this one on this pin module, we will be considering it as our output. Okay, so output should be clicked, and it should be green, and this one should be orange. So as you can see here, our pin module our pin manager here, which is our package view, will look like this. So now, after setting up our IC, we should go to our pin module. Okay, let's go to our pin module, and after going to pin module, let's check this RE0 here. So since we will be using an analog input, okay, analog should be ticked, okay, and output should not be ticked, and we should rename this. Okay, we should rename this. Okay, port A0. Okay, port A0, and this RE4. Since we selected this as our output, we will be unticking or unclicking analog, but output should be clicked since it's our output, and we should rename this T2. Okay, we should rename this one underscore LED. Okay, so this is our pin module settings for this experiment. So after our pin module, we should go to our system module. Okay, let's click this here, and our oscillator select should be this one, and our HF internal clock should be 4 megahertz, and then low voltage programming should be enabled, and clock divider should be 4. After this one, so after our system module, we should go to ADC module. Okay, so we should go to this part of our Mplab software, and then our clock source should be frequency oscillation here over analog to digital clock. Okay, so FOSC over ADC. Okay, and our clock should be frequency oscillation over 2, and then our result alignment should be right. Our positive reference should be VDD and PSS all, or should not be unchanged. Okay, and our auto conversion trigger should be disabled. So after our ADCC system, we should go to this part, and let's click generate. Okay, so let's wait for it to say that our generation is complete. Okay, generation complete here. And after this one, now we will be going to our header files here under projects. Okay, let's double click this one, and let's open adc.h file here. Okay, and after that, we will be opening pin_manager.h here, and then on our main.c file, we will be encoding our program for our potentiometer. Okay, so make sure that our system is initialized. So let's scroll down, and here under our while loop, we will be inputting our code. Okay, so let's first type the code here, and we will be getting a special variable from our. So we should go to our adcc.h file here. Okay, and we should find for our addc_get the single conversion. Okay, program here. So let's find it. Let's scroll down. So we should get conversion. Okay, get single conversion. This one. So we should select and copy this one. Okay, let's copy this, and then we will be using this on our main.c file. So let's go to our main.c file, and let's put it here. So now we will be modifying our code. We're in. Okay, let's type our code here. We're in the potentiometer. We'll be considering. Okay, we'll be considering a low and a high value when we adjust its knob, just like what I've explained a while ago. So I've corrected the name of our potentiometer to pot. Okay, so it could be identified as our pot. So as you can see here, the name of our potentiometer here is pot underscore A0. So let's go back to our main.c file. So put underscore dot A0. So let's put it here. You will be encoding our program. So let's put the value 512, which is half of the value of our potentiometer value that I will be explaining later on. So let's put our bracket here, and then we will be putting another program, which, just like what I've said a while ago, we will be programming our microcontroller, wherein it will be setting a value, okay? It will be setting a low and a high value for our potentiometer. So this one is for the high value, and for the second one, if the condition is not satisfied, so let's put an else statement here. If it's not satisfied, then let's put another bracket here. We will be setting another value, which is the low value here. So set low, and then so let's remove the semicolon here, and let's correct this code here. So let's put a space in here. So this is our code for our potentiometer. So to explain this code, explaining the AD's result will produce a value between 0 and 1023 depending on the position of our potentiometer. A value of 0 is the position all the way counterclockwise. A value of 1023 is all the way clockwise. The halfway point is a value of 512. So just like what I said earlier, this is the half value of 1023. So with this half value, we shall test the position by comparing the value to 512. Meaning, if it is larger than 512, then the LED will be lit, okay? Or the LED will be light up, or it will be turned on, okay? Because our program here is D2 underscore LED set high, okay? Else, if the condition is not satisfied, if our potentiometer is less than, okay, or smaller, smaller or equal to 512, then the LED will be off. Just like what you can see here, our program is the LED will be set low. So that's the logic behind our source code. Now after this one, we will be clicking this hammer here, which indicates that we will be building our program. So let's just wait for it to build successfully. Okay, build successful. So now we will be going to our Mplab IPE to connect our PICA3. So now we will be using our Mplab IPE. So let's connect our PICA3, make sure that it is connected, okay, and it is recognized by our Mplab IPE. Then let's just wait for it to recognize and connect our PICA3, okay. So as you can see, enhance mainframe. So in this part, we will be editing our settings, okay. So let's go to advanced mode, and then let's type the password, which is microchip, and then let's go to our power here, and then let's select 3.125, and then power target. Circuit from PICA3 should be ticked, and we should browse our hex file here. So our hex file is on this folder, Digital Lab 2, and then Analog Input Casabuena X, and then this, and then Default, and then Production, and this hex file here. So let's click Open. Okay, hex file loaded successfully, so let's click Program. So as you can see, there is a pop-up saying Programming Complete. So now we will be constructing our circuit. So just like what I've said a while ago, we already connected our IC, okay, our microcontroller to our PICA3, and we already connected our PICA3 to our Mplab IPE, okay, it's already on the active status, and our IC has been programmed already using our source code that we made in our Mplab IDE. So now we will be constructing the actual circuit. So now let's construct our circuit. We will be using a 10 kilo ohm potentiometer, okay, as our analog input. So we will be putting it here, okay, let's connect it here. So make sure that it is connected properly, okay. So this first terminal of our potentiometer, we should connect it to our positive supply, okay. So let's connect this one. Let's connect it to our positive supply, or to our 3 volts terminal here, and then so our second terminal of our potentiometer should be connected, okay, since it's quite long. It should be connected to our RE0, okay, or our IC pin for our potentiometer, which will be our analog input. So it's on pin number 2 of our IC. So let's connect it here. And then the third terminal of our potentiometer should be connected to the ground. So let's use a gray wire here. So let's connect it to the ground. Okay. So for our output, we will be using, okay, a red LED here and a 360 ohm resistor, which is connected to our RE4, or the pin number 6. Okay, let's use a green wire here. Pin number 6 of our IC. So let me count. 1, 2, 3, 4, 5, 6. So this here. Okay, let's connect it to the pin number 6. So let's put it here. And then let's connect an LED. And let's connect a series resistor to our LED. So let's connect it here, here. And then the negative terminal of our LED should be connected to our ground. So let's find a gray wire here. So let's connect this one to the ground. And after that, do not forget the proper connection, okay? The proper connection of our VDD and VSS. So VDD, so our orange white here is our connection for our VDD, okay? So this should be, so this will be on our positive terminal, okay? Let's put it here. And then our VSS, which is on the 12 slot, okay? This black wire here should be connected to our ground, okay? So let's connect it to the ground. And then on the other side, let's connect the VDD again, okay? It's on the 30 seconds slot pin. So 40, 39, 38, 37, 36, 35, 34. So on the 30-second slot or pin, VDD should be connected to our positive terminal. And then let's find a gray wire here, okay? And our VSS is connected to our ground, which is on the 31st pin of our IC. So this is what our circuit looks like, okay? So this is our potentiometer, then this is our LED, okay, the red LED, and the right connection. So please make sure that your connection is correct, because if your circuit is not properly connected, let's say a ground is missing, then it will not be working. So now, since I've already connected my power supply through my power module here, let's turn on our power supply, okay? So now we will be testing if our source code is correct, wherein it will enable us to convert our analog input using this potentiometer to digital input that can be recognized by our microcontroller here, which will let our LED be turned off and turned on as well, okay? Meaning, if it is turned off, it should be on logic 0, okay? So our analog signal here is already converted, if it worked, and if it's on, it is on logic 1, okay? Meaning, there is a voltage flowing on our circuit, okay? And there is a current as well. So now, our power module is already on, so let's move our potentiometer to the right, just like what we've explained a while ago. If we move it to the right from its center, it should turn on, okay? So let's try it. Okay, as you can see, if we move the potentiometer to the right, okay, meaning the value of our resistance is greater than 12, okay, I mean, is greater than 512, the LED will turn on, just like what you are seeing here. But if the value of the resistance from the potentiometer is equal, okay, is equal or less than 512, then our LED will be turned off or will be set low. So this allows us to convert an analog signal from this potentiometer, okay, to digital signal that can be processed by our microcontroller, giving us a digital input that will be conveyed through digital output through our LED. So that's one of the application of our analog to digital converters, which is really essential in programming and in setting our electronic components and circuit boards. So that's our experiment number 5. I hope you learned something from our experiment today, and I hope I will be seeing you on our next episodes and vlogs for digital electronics. So keep safe and God bless us all.